I am Mishra, and the present work is on chaotic signal generation in Colpitts oscillator and its modification by Diode-Varactor to achieve enhanced spectral range and overall output power of chaos. For the chaos communication, the much needed thing is chaotic signal generator for modulation and demodulation applications with desired features like high frequency range of operation in RF and microwave range, high spectral bandwidth, high output power. The chaotic signals having their property used in encryption is initial condition sensitivity, and broad spectrum is used to generate spread spectrum signals. Here is the block diagram of chaos communication. Transmitter. Before transmitter, the signal is modulated over chaotic carrier pulse data, and at the receiver end, the chaotic pulse data gets separated and recovered data is found with additional feature of chaos communication or additional benefit of chaos communication. Here is the modification that is done to the standard Colpitts oscillator. The modified Colpitts oscillator shown on right side. The standard Colpitts oscillator have only single nonlinearity of B junction of the transistor. As well, the standard modified Colpitts oscillator have two nonlinearities: the IV nonlinearity of B junction of transistor and diode-Varactor capacitance, that is nonlinear and exponentially decaying nature of this type. The square box, the dotted square red box here shows the modification that is done to the standard Colpitts oscillator is static C1 get replaced by combination of back-to-back added Varactor diode. This modification is simple and effective for the spectral enrichment and power boosting, and it is shown in further slides. The tools that are incorporated to support the analysis of the circuit is enlisted here. First is state space description of the oscillator circuit, determination of fixed point and Lyapunov stability around it, bifurcation diagram, phase portraits and power spectrum by FFT. By applying KVL and KCL to the modified circuitry, we have found three coupled differential equations as my state equations with linearly independent variables VC, VB and IL. VC is nothing but voltage drop across static capacitance or output static capacitance C1 in the modified circuitry. VB is the voltage drop across C2, and IL is the current flowing through only inductance in the circuitry, that is L. The IV nonlinearity of the transistor DFG 520 NPN is mathematically modeled as piecewise linear formula, that is the base current IB is equals VB minus VTST divided by R on is the dynamic resistance of the junction B junction, VB is the voltage drop across B junction, and VTST is the threshold voltage. The nonlinear capacitance of SMV 1493-011 Varactor diode is mathematically modeled as C1 equals C0 1 plus VC divided by VTSD to the power minus M. The C0 and M are numbers and corresponds to zero bias capacitance. M is deciding the power law. VC is the biasing voltage to the Varactor diode, and VTSD is the threshold voltage of the junction. The state equation 1, 2, 3 is solved to find the two fixed points corresponding to transistor off state and on state. On the left side there is fixed point VC, VB, IL at the biasing voltage value, initial biasing value, and corresponding to the on state, here VC, VB, VC, VB and IL value for the on state. For analyzing further the Lyapunov stability around these two fixed points, we have calculated the real part of Lyapunov exponent by using LET toolbox in MATLAB based on Wolf algorithm for a range of varied load resistance 1 to 100 ohm RL, keeping other optimized parameters for the circuitry constant and listed over here: beta, R on, ADS, DVC, all. The Lyapunov exponents for the standard and for the modified circuitry is plotted above and below. The blue line is showing one of the Lyapunov exponents, with other two Lyapunov exponents, green and red, are negative and one is positive throughout the range of RL. Similarly, no qualitative change here also after modification. One Lyapunov exponent is positive, with other two Lyapunov exponents are negative. That one positive Lyapunov exponent shows the chaotic nature or suggests the chaotic nature of the circuitry throughout the RL range in both of the systems. The corresponding bifurcation diagram for the same RL range is also drawn. That is nothing but the output voltage or selected output voltage based on a criteria plotted against RL, the load resistance, whole range. These are the chaotic windows that shown by this arrow, and the instantaneous value for chosen for the further analysis is 19 ohm, 35 ohm and 50 ohm. Correspondingly, for the shifted parameter range, the 21 ohm, 45 ohm and 64 ohm for the modified circuitry. Moving on to the phase portrait, the left side is shown as standard for the standard Colpitts oscillator. The chosen parametric range is 19 ohm, 35 ohm and 50 ohm, and the plot is VC versus VB, the output voltage versus input or feedback voltage. Similarly, for Varactor modified system, the parameter range is investigated parameter range is 21 ohm, 45 ohm and 64 ohm. Here we can see the trajectories are denser and attractor side is increased. Attractor size or dimension is increased after modification. Here is the power spectrum of standard and modified system for the chosen values of load resistance. Shaded region on left is approximately half of the shaded area on the corresponding plot right side. That suggests overall power gets doubled after modification. If we focus in the 6 to 8 gigahertz frequency range in all plots, we get more fluctuations visible on right side than on left side. That suggests the modification helps high frequency generation in the modified system. In support of previous finding, we have also calculated integrated power numerically for standard and modified system, which is area under the power spectrum curve for the chosen values of load resistance corresponding to 3 different frequencies shown in this table. Ratio is around 2 in all cases. That confirms the power doubling after modification in the standard system. These are the conclusion of my presentation. Using Varactor diode in modification of standard Colpitts oscillator help it to generate high frequency chaotic output signal. Power spectrum and integrated power analysis shows almost doubling of the overall output signal power in modified circuitry. The power levels in both standard and Varactor modified oscillators, however, increase with reduced losses at lower load resistance. I would like to acknowledge UGC and CSR for providing fellowship. Thank you.